Today we will discuss about the torque acting on a current carrying loop in a uniform magnetic field. Consider a rectangular loop of height L and width B carrying a current I. The axis of the loop is perpendicular to the uniform magnetic. We have applying a magnetic field in this direction. This is the axis of this coil. So this magnetic field is perpendicular to the axis of this magnetic field. We have drawn a normal to the plane of this coil. This plane is placed in a slanted position. So this is the normal to the plane of this coil. So this normal makes an angle theta with the direction of magnetic field. We have to find out the forces acting on this direction along the side 1, 2, 3, 4, etc. So we will find out first in the opposite sides 1 and 3 and then 2 and 4. In the opposite sides, the forces acting are marked as F1 and F3. This is side 1 and this is side 3, and these two sides are F2 and F4. Forces acting on these sides 2 and 4 are F2 and F4. The forces acting on the bottom and top sides, bottom side 1 and top side 3, top sides 1 and 3 are F1 and F3. They are equal, opposite, and set along the and act along the same line. F1 is equal to minus E into V cross B. F1 is equal to, this is according to Lorentz equation. Whenever an electron is moving in a magnetic field, it experiences a force, magnetic Lorentz force, and which is equivalent to a current. Let the electron move with a velocity v in a direction perpendicular to the magnetic field. Let the electron move a distance L in time. Then the time taken for its travel will be L by V. V is the velocity, L is the distance traveled, so the time taken will be L by V. So that the current can be written as I is equal to, the current we will written as E by T, that is charge by time. So instead of T we can substitute L by V. So we will get I is equal to EV by L. Here current is along path 1 of breadth B. Current is this current. Now the force F1 is equal to minus E. Instead of V we can substitute B by T, because the distance traveled here is L. Distance traveled here is L along the side 1. So we can substitute B by T here. So this will become minus E by T into B cross B. E by T is I, so I into B cross B. Now the modulus value of the force F1 can be written as mod value of I into B cross B. So this will become B cross B means B into B sine and the angle between B and B. What is the angle between B and B? Here this is side 1 and this is side 3. The angle here between, this is the direction of B and this is the direction of B. So the angle between B and B is 90 minus theta here. 90 minus theta here, because this is the normal. This is the normal drawn to the axis, to the plane. So this angle will be 90 and this is theta. So this angle will be 90 minus theta. This is along along the side 3. And what will be the angle at side 1? side 1, just the angle will be 90 plus theta. Okay, because this direction of B is in this direction, opposite to this B. So this is the angle will be, the direction of B is along this direction, so the angle is this, so this will be 90 plus theta. You can draw a separate picture to verify this. So this is 90 minus theta and this is 90 plus theta. If you are substituting these values here, along side 1, this angle is sin 90 minus theta, and the bottom side, so this is sin 90 minus theta is equal to sin 90 plus theta is equal to cos theta. So we will get IBB cos theta. Okay, but by the vector product rule, this force is upward on the top side and downward on the bottom side. So if we take the this is a cross product B cross B. So if we take the directions of this B cross B direction along the bottom side, we will get z cross x direction, that is in minus y direction along y at the bottom side, and y direction in the minus y direction in the bottom side and y direction in the top side. By we have B cross B in the equation, so minus z cap cross x is equal to minus y cap. This is along this is at the bottom side, and z cap cross x in the top side, so the direction will be y direction. So this rule, the forces acting upward on the top side and downward on the bottom side. The net force on the rigid loop from these elements is the zero, as is the torque. So these forces on the top and bottom sides are acting opposite to each other. They are equal and opposite and acting along the same line. So this will cancel each other. The net force will be 0 due to F1 and F3. Now we have to find out forces acting on the vertical sides 2 and 4, F2 and F4. So we are applying the same rule, same method here to find out the forces acting between the sides 2 and 4. They are equal and opposite but do not act along the same line. That is, this is side 2 and 4. These forces will be acting along the same in the equal and opposite but do not acting along the same direction, and the magnitude will be, and its magnitude will be IL into B, as here IBB, because the length of that loop in the top and bottom side is B, that is why B here, and here it is IL because the length of the loop is here L, and the angle between B and L is 90. So the force acting on this direction and this direction is along different lines, and the angle between magnetic field and the current will be along is 90 degree, that is perpendicular. So sin 90 is 1, so the magnitude will be IL into B. These two forces produces a torque, that is force is equal to minus IL cross B, which is equal to I sin 90. So we will get ILB. So that's what we said here, ILB. Okay. Now the torque can be written as the moment of the force. So ILB sin theta. ഈ ILB sin theta, L into B can be written as A, which is the area of the loop. So we can written as the torque acting on this torque acting on this loop is IAB sin theta, which is due to the forces acting on the sides 2 and 4, because there is a net force due to the forces on the sides 2 and 4, no net force due to forces acting on the top and bottom sides. If there are n turns on the loop, torque can be written as NIAB sin theta, and n is appearing here if there are n number of turns in the loop. We define the magnetic dipole moment of a plane current loop as mu is equal to this is a magnitude value, this is mu, which is equal to area into current. This is equal to n into I into A, where n is the number of turns in the coil. So the torque can be written as mu cross B, which is equal to mu B sin theta. So here NIA is equal to mu. So torque is mu B sin theta, which is mu cross B. So we will get tau as mu cross B, which is mu B sin theta. The direction of mu is given by the right-handed screw rule. Right? You know what is right-handed screw rule? That is, if we are holding if we are turning a screw like this, what will be the direction of mu? The direction of mu will be the advancing direction of the screw. The moving coil galvanometer based on this concept. Okay, so this is about the torque acting on a current carrying loop in a uniform magnetic field. The moving coil ballistic galvanometer is working on this principle, that the torque acting on a current carrying loop. We will discuss it.